Imagine teaching a dog to fetch a tennis ball. Now, you want to teach it to fetch a frisbee. The dog already understands basic commands and the concept of retrieving. This prior learning makes mastering the frisbee much easier. This, in essence, is transfer learning in the world of artificial intelligence. Transfer learning is a clever technique where an AI model trained on one task applies its knowledge to a different but related task. Instead of starting from scratch, the model leverages its existing expertise, accelerating the learning process and often boosting performance on the new task. Think of it like this. You wouldn't learn to ride a bike from scratch after mastering a motorcycle. You'd transfer your knowledge of balance, steering, and coordination. Similarly, transfer learning allows AI models to leverage pre-existing knowledge for faster, more efficient learning. This approach is particularly useful when training data for the new task is scarce or expensive to obtain. By tapping into the wealth of knowledge from a previously trained model, we can overcome these limitations and achieve impressive results. Now, where does transfer learning fit in the grand scheme of AI? Is it a deep-sea creature of deep learning, or a surface swimmer in the pool of general machine learning? Transfer learning primarily finds its home in the depths of deep learning. Deep learning models, with their intricate layers of artificial neurons, are particularly adept at learning complex patterns and representations from vast data sets. These learned representations, often capturing general features and concepts, prove incredibly valuable for transfer. It's like learning the alphabet. Once mastered, it forms the foundation for reading countless words and sentences. However, don't relegate transfer learning solely to the realm of deep learning. While it shines brightest there, simpler machine learning algorithms can also benefit from its principles. Let's explore a step-by-step process of transfer learning using a decision tree model and a random forest model combination. First, we train a decision tree model on a source task, such as classifying types of flowers based on their features. Next, we take this trained decision tree and use it as a base for a random forest model, which is an ensemble of decision trees. We then fine-tune this random forest model using a smaller dataset related to a target task, such as classifying different species of plants. This process leverages the knowledge gained from the decision tree model to improve the performance of the random forest model on the new task. Imagine a spam detection model trained on emails. By transferring this model and fine-tuning it with a smaller dataset of text messages, we can create a spam filter for SMS, showcasing the versatility of transfer learning. From filtering spam to revolutionizing healthcare, transfer learning is leaving its mark across industries. Let's explore some real-world examples where this powerful technique is making waves. Ever wondered how your phone effortlessly tags friends in photos? Transfer learning is the magic behind it. Models trained on massive data sets of images like ImageNet can be fine-tuned to recognize specific faces or objects with remarkable accuracy. Think chatbots, language translation, and even auto-completion tools. Transfer learning powers these applications by enabling models to understand and generate human-like text based on prior training on vast text corpora. Transfer learning is transforming healthcare by assisting doctors in diagnosing diseases earlier and more accurately. Models trained on large data sets of medical images can be fine-tuned to detect specific conditions like cancer in new patient scans. These are just a glimpse into the vast potential of transfer learning. As research progresses and models become more sophisticated, we can expect even more innovative and impactful applications to emerge. While transfer learning opens up exciting possibilities, it's not without its challenges and limitations. Understanding these is crucial for effectively harnessing its power. One key challenge is negative transfer, where the knowledge transferred from the source task actually hinders performance on the target task. Imagine trying to teach a fish to climb a tree based on its swimming skills. Not very effective. Another challenge lies in selecting the right pre-trained model and the appropriate layers to transfer. Choosing poorly can lead to suboptimal results or even introduce biases from the source data. Finally, data bias poses a significant challenge. If the source data contains biases, these biases can be inadvertently transferred to the target task, leading to unfair or inaccurate predictions. Despite these challenges, transfer learning remains a powerful tool in the AI arsenal. By carefully considering the task, data and potential biases, we can overcome these hurdles and unlock the full potential of this transformative technology.